Buenas tardes. I think it's the right time for this, I hope at least. I would like to tell you a little bit about the Rosetta mission, of which I guess you all have heard. But before I start to talk about Rosetta itself, I want to give you a brief overview of comets, because this is what Rosetta does. It rendezvous with a comet, and it will find out all about this comet, all the secrets it has tried to hide from us for so many years. So let's start with an overview of what is a comet. I will make this very brief. This is a typical comet as you see it in the sky. And what you see is that the comet is composed of three different parts, which is the cometary atmosphere, the dust tail, and the ion or plasma tail. But actually, you don't see the real comet as such. You don't see the comet nucleus. So in here, in the cometary coma, the comet atmosphere, is a tiny nucleus of order of 1 to 10 kilometers in size, in diameter, and that is a frozen dust ball. And when this frozen dust ball comes close to the sun, on its orbit around the sun, then the gases, the frozen gases will evaporate, come out of the comet nucleus, drag the dust in it with it, and then they form this coma here, the comet atmosphere, which is about 100,000 kilometers in size, and both tails are formed, the dust tail and the ion tail, which are even larger. This is about 1 million kilometers, and this can be as long as 10 to the 8th kilometers. So the material comes out of the nucleus, which you see here. This is the picture of Comet Halley, the first comet nucleus that was ever visited and photographed. And maybe I go back to this, and you see here that the material comes out here on the sunlit side. The sun would be over here. And then from this material coming out here, the coma and the tails are formed. Very briefly, how are they formed? Well, the gas and dust coma is simply formed by the material coming out, which is at the time neutral. And then, due to solar radiation pressure, the sun on this comet is here, opposite to the ion tail. Due to solar radiation pressure, the dust particles will slowly, piece by piece, be moved away from the comet and will stay on the orbit of the comet. So this would be the orbit of the comet around the sun, and will be on their own orbits around the sun. And so they build the slightly tilted dust tail, and the ion tail is formed out of ions, as is clear from the name. The material gets ionized by the sunlight, and then the solar wind drags it into directly anti-solar direction. So this is what we see in the sky. This is the nucleus from which this all comes from, and it gets even better. If we would be able to see in Lyman alpha, then we would be amazed, because this picture is on scale. You see here a photograph of Comet Hale-Bopp in Lyman alpha, taken with the Solar and Heliospheric Observatory of ESA with the SWAN camera. And this is the picture that you just saw. This is the typical size of the comet, something like 10 to the 8th kilometers in size for the ion tail. And this is what you would see if we could look in Lyman alpha. This is 30 degrees in the sky. We would all be scared, very scared. So, but coming back to why are comets scientifically important, comets are believed to be relics on the early solar system. They are believed to have been formed at molecular cloud temperature at the time the solar system formed, so at temperatures smaller than 30 Kelvin. And they were stored at low temperatures, below 50 Kelvin, during the entire lifetime of the solar system. They are either stored in the Oort cloud or in the Kuiper belt, which is a belt of comets, which is the source for the short period comets outside the Neptunian orbit. The gas phase molecules of comets are known to be similar to the interstellar abundance, and we believe that comet material reflects the composition of pre-solar nebula. In addition, comet nuclei should contain the most pristine material in the solar system and large organic molecules. So from this, we believe that Comets will provide the ultimate clues on the formation and evolution of the solar system because they allow a view into the past of the solar system at the time of the very formation. And I want to give you one example that underpins my two sentences about gas phase molecules similar to interstellar abundance and also that coma material reflects composition of pre-solar nebula. What you see here is a spectrum in the infrared that was obtained by the ISO, the infrared satellite of ESO, in 1997 of comet Hale-Bopp and of a circumstellar disk, HD 100546. This is the comet here, and this is the circumstellar disk. And you see very nicely that these two spectra resemble each other very well. You see here the silicon band at 10, you see the 20 silicon band, but you also see other bands that resemble very well. Of course, this is phenomenologically for a large part because we are talking about infrared spectra and we see only then the rho vibrational bands of the bindings of molecules, but it was remarkably similar and shows that there is clearly a connection between comets and circumstellar disks, so the predecessors of solar systems or planetary systems. In cometary science, there have been two major leaps in the past 25 years. One of those was when ESA's Giotto mission went to Comet Halley. On 13th of March 1986, the Giotto probe flew by Comet Halley in one day and took the first ever picture of a comet nucleus. And this is important because before that, we did not really know whether the comet is a solid body or whether it is composed of rubble piles in the way that the sandbank model that at the time was still in discussion is valid. So now we know a comet is a solid body. In addition to finding out this, the Giotto mission found out a great deal of the composition of comets. Particularly, it showed that the dust particles in comets have very small dust particles. They include very small dust particles, which are composed of carbon, hydrogen, oxygen, and nitrogen, the so-called Schonn particles. And so we know now that there are large organic molecules in comets. We do not know the details of these large organic molecules, but after Rosetta, we will have a much better clue about this. So the second leap in cometary science was not actually connected to a space mission. Let me see where, no, this does not work. What a pity. There's supposed to be a film here which you don't see now. You would have seen it on the computer, but it's just a comet rotating around the sun and getting active and inactive again. So what we have here is the second leap in cometary science, which had to do with two things. That comet Hale-Bopp was discovered at a distance, incoming at a distance of 10 astronomical units. And so it was the first time we could observe a very large comet from far out coming in and monitor it on its way in, and so on its way in, coming from here, and out again to 10 astronomical units. So we could see how it developed and how the composition of the coma and the tails changed as a function of time. And that is very important because I showed you the Giotto mission, and there are other missions to comets, but they are always only flybys. That means the comet is at a certain position, let's say here, then a spacecraft comes, flies by, and then it takes as much data as possible during the short time that it flies by the comet, and then the mission is over. So it has only a glimpse of what the comet looks like along its orbit. So for Hale-Bopp, it was possible to look at the evolution of the comet along the part of the orbit where it was most active. In addition to this, sub-millimeter telescopes were just developed to a level that we could actually look into organic gas molecules. You see here on this side that we have things like methanol or formaldehyde, we have HCN, we have CH3CN, and we also have OH resembling the water and carbon monoxide. And we now have this is the production rate, and this is the heliocentric distance going inbound to here. This is perihel, and going outbound here. So we have of each of these species the production rate as a function of heliocentric distance coming in and going out. And from this, we can see whether there are things that are different when the comet comes in and when it goes out. I'm not going into detail here because we want to move on to Rosetta, but I want to point out one point here, which is this one. This is the most important point on the entire view graph, because what you see here is the black dots are OH, so they resemble the water production rate as a function of heliocentric distance, and the green dots here are carbon monoxide. And at this point, at 3 astronomical units here, oops, somewhere here, they cross. That means that outside these 3 astronomical units, the CO is higher in abundance than the water, and means this gas drives the activity. I told you earlier that dust is coming out of a comet nucleus, and it has to be dragged out by something, which has to be a sublimating gas. And in this case, it is not the water, it is the CO. And then at 3 astronomical units, the water takes over as the driver of activity, and actually a comet is composed to 90% of water. So we see that the 10% CO or 9% CO it has is very important when further out. And we also see from this how important it is to observe a comet along its orbit and not just have a snapshot at one position. So to summarize again, we have here the typical features of a comet and the dimensions. We have the nucleus, the coma or comet atmosphere. The nucleus is about 1 to 10 kilometers, sometimes maybe 20 kilometers. The coma is much, much larger, in the ballpark of 100,000 kilometers to 500,000 kilometers. The dust tail gets about 1 million kilometers, and the ion tail can get as large as 10 to the 8th kilometers. And then, of course, we have the huge hydrogen envelope. So one sees already, to design a single space mission, you need to select, first of all, the right comet, but you also have to have very focused objectives, because you can't do it all, simply because of the dimensions. And so for Rosetta, the following design was picked. We have a nucleus mission, so we want to look at the comet from which all this comes out. We look already at the nucleus, and we look into the near nucleus region from 1 to 10 kilometers, which is where the density of the molecules is still so large that it comes to collision, so we have chemistry there. And then we look into the inner coma of the comet, smaller than 1,000 kilometers, where it's already starting to be collisionally free, and so then we can compare this also to the coma further out. And all this is done as a function of heliocentric distance. So what is Rosetta? We see here that Rosetta is a mission that goes in orbit around a comet nucleus, and it will land on a comet. The comet is active here. You see this in this animation what Rosetta is about. So I will now very briefly look into the mission, the spacecraft and lander, and why this is interesting for you. First of all, the target. We go to Comet Churyumov-Gerasimenko, which is a short period comet of the Jupiter family, which means that its aphelion, so the furthest point to the Sun, is close to Jupiter. It has an orbital period of about 6.5 years. The perihelion is at 1.24. Aphelion is at about 5.7 AU. And it was discovered in 1969 by Mr. Churyumov and Mrs. Gerasimenko. And this is the discovery picture. So this is the comet as discovery. Here you see the orbit of the comet. It goes in this direction. And Rosetta has actually met it somewhere here. Yeah, at 4.6 astronomical units. It spotted it and went for it. And it's now in orbit around the nucleus. You see here a picture obtained in 2003 with the VLT Force telescope, and you see what the comet looked like there at 3 astronomical units, so it was active then already. Now the milestones of the mission. The mission was launched on 2nd of March 2004 with an Ariane 5 at Kourou in French Guiana. And it had a rather long journey. It had to do a number of maneuvers and gravity assists, 4 deep space maneuvers, 3 Earth gravity assists, and so on. I go through this in a bit more detail later, but I want to say that these things, the deep space maneuvers and the gravity assist, had to be made because we do not do a flyby, we go in orbit around the comet. And that means that we have to have the same velocity as the comet has around the sun when we reach it, otherwise we can't go in orbit. And that is very difficult because no rocket on the Earth can give us this velocity. And therefore we had to do all these gravity assists to actually get angular momentum, speak velocity from the planets to end up with the velocity we need to be at the same velocity as the comet at arrival to actually be able to go in orbit. And this is why why only flyby missions have been done before, because this is easy. The comet comes from one direction, the spacecraft come from one direction, and then they pass by each other with completely different velocity vectors, and then the mission is over. But this one is different. So, after launch, we had, let's now hope that this works. After launch, we had deep space maneuvers to get us in the right orbit, and then we had altogether 3 gravity assists at Earth. Here you see this resembled in a film. The first was in March 2005, then one in November 2007, and one exactly 2 years later in 2009. After the March gravity assist in 2005, we went to Mars to have a gravity assist there. And actually, that is the first and only picture that was ever taken of a spacecraft in orbit around Mars. You see here the Rosetta spacecraft taking a selfie, so to speak, with its mobile phone and in orbit around Mars. Why could it do it? Because Rosetta has an orbiter and a lander. So while the platform with all the payload was pointing towards the planet, the lander was on the other side, the camera was switched on, and then it could take a picture of the spacecraft with the camera that was not pointing to Mars. Then after each of the Earth flybys, in November 2007 and in November 2009, we took the opportunity to fly by an asteroid in the asteroid belt because we had to take an orbit out and come back to Earth. So we thought that we can as well take advantage of that. We have to do ping-pong billiard in the inner solar system because we have to do the gravity assist and do some science in the asteroid belt. And here you see what this looks like for Steins, hopefully. So when I start here, you have to imagine that the spacecraft just did a gravity assist at the Earth, and it's now, oh, it doesn't work, no. Let's try one more time. It will work. Yeah. And so it's on its way to Steins. You see Steins coming up here, asteroid Steins. And now it passes by the asteroid. That vanishes then wherever it goes, and the spacecraft returns to Earth for its next gravity assist in 2009. And then after that, it does something similar and passes by the next asteroid, Lutetia, in 2010. After that, it went further out into the outer solar system and went actually to hibernation, to sleep, in July 2011 for 30 months because it passed by so far out that because it has only solar cells, so no radioactive units for heating or for powering the spacecraft, we had to switch it off for a while until it was further in. So we let it sleep for 30 months. It woke up on 20th of January 2014, so just a few months ago. Then in May, we had the rendezvous maneuver and we're on our way to the comet. And then we will soon have the lander delivery. Oh, I forgot this. I'll show you this in a minute. Soon have the lander delivery. And you see here, this is an animation of the lander delivery. This will be on 11th of November 2014, so soon. Then Rosetta will stay in orbit around the nucleus, go through perihelion passage, which will be in August 2015, and continue in orbit around the nucleus until the end of the nominal mission in December 2015, when the comet is at 1.9 AU outbound already. I forgot this image here. This actually shows you pictures of the two asteroids that have been flown by Rosetta. This is asteroid Steins and this is Lutetia. I can't go into detail there. I only tell you that this asteroid is about 5 kilometers in size, and this is about 125 on the long axis. This was supposed to be the film that I can't show, that would have given you the ping pong of what happens. I will try to do this now without the film. So let's assume here's the Earth. This is the orbit of Mars. So you start here. You first have a maneuver somewhere in deep space, go back to the Earth, have a swing by, go to Mars, have a swing by here, go back to the Earth, have a swing by, pass by asteroid Steins, which is this loop here, go back, have a swing by at the Earth, and pass to asteroid Lutetia, which is this loop here, and then go out to the outer solar system, and then meet the comet about here. This would have been a nice animation, but it was not to be. On the flybys, because I have very little time, just briefly, we flew by asteroid Steins at 802.6 kilometers. It was planned to go by at 800 kilometers, so you see how well this has been calculated. And Lutetia we passed by at 3,168. For anybody who is interested, there are plenty of special issues on these two asteroids with really marvelous results in planetary and space science and also in science. But now let's come back to the Rosetta mission. It is the first mission to orbit a comet nucleus and deploy a lander onto the surface. It will study the evolution of the comet while it approaches the sun and beyond when it's going back. It will bring a full laboratory to a comet for in situ chemical analysis. And it will help to understand if comets contributed to the origin of life and the formation of oceans on the Earth. And it will also help us to understand the origin and evolution of the solar system. So this is the spacecraft. You see here the platform with all the payload. This is the high-gain antenna, and here you see the lander. And this is the payload of the spacecraft. I will not go through it in detail. We have 10 instruments on board. These are all remote sensing instruments from the ultraviolet through visible camera, infrared, and submillimeter. Then we have mass spectrometers for gas and dust analysis. We have comet tomography, which is this instrument here. And then we have a plasma package here and additional instruments for further dust analysis and radio science for getting the mass and the inertia of the comet. In addition, the lander has a whole suite of 10 additional instruments, including cameras and gas chromatograph with mass spectrometer combination, and also instruments that look into the physical properties of the comet. So this is an animation that shows the landing. So we will, on the 11th of November, come on, do it. Yeah, I try it one more time. Come on. It's not doing it. It's really a pity with this.
No, it's not working. I thought we tried this one yesterday.
Yeah, we tried it.
Weird.
Well, if we don't have this, then we miss the best bit. But maybe I continue and show you the landing later, because otherwise I'll be running completely out of time, and now come the results, which you might be most interested in. Is this still on, or is it off?
We try again, real quick. Is this the one now?
No further. This is the one. Yeah, it does it. Thank you. So you see here an animation of the landing. Don't forget the comet has a very low gravity, so it will be difficult. The comet is only some 2.5 kilometers in radius, so 5 kilometers. Now, you see here, the lander gets detached. Then it unfolds its landing gear, 3 legs, and some of the instruments, antennae for some radio instrumentation. Here you see it again. And then it goes down on the surface. And when it hits the comet, it will immediately throw a harpoon down here and have some ice screws to fix onto the comet so that it doesn't bounce back because of the low gravity. Okay, so here you see the lander land, that's a part of the film, and here you see landing sites that have been picked that will be decided by the end of October where we actually will land. So 5 landing sites have been picked, 3 on the smaller bit of the comet and 2 on the larger bit of the comet. And here you see them in more detail. So it will be, so we see them here in more detail, but at the moment they are mapped even further so that we can see better what would be a good site. This is a bit brighter, so there may be more ice. There may be a crust here, so they all have their advantages and disadvantages. It also shows how brilliant the camera works. So I spoke about the mission, the spacecraft and the lander, and now comes why this is interesting for you. I hope I can still do this. I will be really fast. So I give you some first impressions. First of all, the comet at this point in time, there's no lander on it yet, and it is not really active. It is a bit active, but not really active. So we look into what is interesting already with the first results that we have. One example is the onset of activity, which is always a very important thing for cometary science because it explains the physics. Onset of activity in the astronomical sense means to us, because when we observe with telescopes, that's all we have, when is the point spread function different from a star? Then it is active. And this onset of activity was observed recently by the Rosetta camera. You see it here, and here's the onset. So we have covered it here. And this could have been done by a telescope, by the VLT just as well. And you see here an enlargement, so the comet is active. On 30th of April 2014, at 4.1 AU, the activity was measured. But now we also, from the Rosetta spacecraft with the sub-millimeter instrument, have for 6th of June a measure of the water production rate. The comet looked like this at the, oops. What did I do? Oh, the comet looked like this at the time, so it was even less active. Now we can combine the water production rate with the dust that we see here, with the activity of the comet, and from this we understand the physics of activity at the comet and also of activity of the onset. So we can compare the water production rate with what is needed to drag out the amount of dust we see. So this is an application that is required so that we later, because we have just one mission to a comet, we later need to take what we learned from the mission and apply it to other comets that we can only see with telescopic observations. Second example is the comet dimensions and rotation. We see here a typical light curve of a comet obtained with telescopes. And from this typical light curve, we get the dimensions of a comet depending on whether we assume prograde or retrograde rotation, and you see it's of order of 5 kilometers by 4 by 3.5, and we get a rotational period of a bit more than 12 hours. And when we see the Rosetta rotation, we see that the 5 kilometers are quite well in the ballpark, and also the rotation is very good. But the real challenge is that if we have interferometers, we can maybe see something like this. This was obtained with Rosetta, but when we have better telescopes where we can, with an interferometer can resolve the nucleus, we can get rotation periods also with a method like this. And now finally, this is really, we look into more details, the comet nucleus shape. This shape model was published in 2006 on the basis of the light curves, and it's a major effort to combine the light curves with the rotational period and then get such a model. And when we then look at the comet, it might look very different, but does it really? I think not. If you look at this picture and tilt it a bit, and then you look at a picture of the comet. First of all, the size is okay. And when you then look at it in more detail, you see that this bit is the only bit which is different. And when you move it on, you see the model is such is not so bad, but this bit is not correct. And it's not correct because there you have a higher albedo than on the rest of the comet. Because for the model, you can assume only, or it was assumed that there is a constant albedo over the entire nucleus. However, we see that there are albedo differences. There are darker spots and lighter spots. And this is also supported by measurements of the temperature of the nucleus. The overall temperature of the nucleus measured by the Virtus infrared spectrograph is minus 70 degrees C. And this is 30 degrees higher than it would be for pure ice. So we have some dark crust material, and we probably have ice here, or at least a high albedo feature. So we see that we can look into why are our ground-based models not correct. I can stop here, or I can do my last one. You decide this. I stop? Okay. So then think of that you can verify a number of properties from telescopic observations when you have a space mission, and in particular coma chemistry models, and that also has astrophysical applications when you look into star formation and when you look into extrasolar planet atmospheres. We have planets here, we are going with spacecraft, so you can compare this here. And that's then the final thing, and there's a film running while I go off. Okay.
Okay, so after this very interesting and accidental presentation, questions. Any question from the public? Yeah?
Could you tell us about the instrumentation that Rosetta has to diagnose organic molecules?
Yes, we have on the lander something which is a mix between a GCMS, gas chromatograph combined with a mass spectrometer. And so we fractionate, we take material, we take samples out of the comet up to 20 centimeters deep, and then we analyze them with this GCMS. First, we fractionate it with the gas chromatograph so that we have already a bit less chaos in our sample, and then we go through the mass spectrometer, and there we can look into large macromolecules and can then identify what organic species are there. In addition, we have something like this on the orbiter, particularly for the dust, where we also look into large organic molecules in the dust phase.
Okay. One final question.
Yeah, here. Will you be tracking the proofs with VLBI during the descent?
With what?
With VLBI, with very long baseline interferometry.
No, we will. There are some observations from ground that will go in parallel, but this is not planned. Although I think it would be a very good idea, but it's not for us to decide whether this will be done, unfortunately.
Okay.
Okay, so let's thank our speaker again.